All right, so thank you for the introduction, Jessica, and I want to thank the organizers for organizing this wonderful event. And it's my honor here to tell you something about the bumpless pipe dream analog of two classical stories on pipe dream. So this talk is about Schubert calculus and then, and then in Schubert calculus, we use pipe dreams and bumpless pipe dreams to go ahead and compute something called the Schubert polynomials. And the pipe dreams are the things up there. They're more classical. There are some very lovely stories on pipe dreams. And then these bumpless pipe dreams are relatively new. And my job today is to give you analogs of those two lovely stories on bumpless pipe dreams. So pipe dreams and bumpless pipe dreams can compute something called the Schubert polynomial. So these are polynomials indexed by Sn, so permutations from Sn. So they came from geometry, and then, thank you. And then the first definition by Lescouture and Berger is recursive. So the base case happens to be when the permutation looks like n minus 1 all the way back to 1. We call it the W0 permutation. If that's the case, then your Schubert polynomial happens to have just one term in it, just that monomial. Otherwise, well, we can just use our partial I operator, the divided difference operator, to compute the other Schubert polynomials. And then this operator, if I apply it on f, well, I have this formula right here where SIF means I'm switching all the xi and xi plus 1 in my polynomial. This is what happens if I apply the partial 1 on x1 squared x2. I'm getting x1, x2. So here's how I can compute the Schubert polynomials in S3. So my first draw a graph on the left. In this graph, I have all these permutations in S3. On the very top, I have the W0, the 3, 2, 1. I can go down an edge by switching two adjacent numbers if the number on the left is larger than the number on the right. So I can go from 3, 2, 1 to 2, 3, 1. I label this edge by T1, 2 to record that I'm switching the first and the second number. Correspondingly, on the polynomial world, the Schubert polynomial of 3, 2, 1 happens to be x1 squared x2 by the base case. And then if I take the T1, 2 edge and go down, correspondingly, I just apply the partial 1 operator. That brings me x1, x2. So the Schubert polynomial of 2, 3, 1 is x1, x2. You can compute Schubert polynomials this way, but this is a combinatorial talk, so we want to see some combinatorics. Bergeron and Billy gave this pipe dream formula back in the 90s. So now they're looking at a staircase grid where we have m boxes in the first row, and then each row will have one last box in the previous row. And then the rightmost tile on each row must be, sorry. Okay. All right. I'll just continue from here, and then the rightmost tile on each row must be this elbow tile. And then everyone else can be a crossing or a bump. But somehow let's just remember that in today's talk, we don't want to see this double crossing. That's evil. Like these two pipes are crossing more than once. That should not happen in this talk. And then these are honestly good pipe dreams right here. And then for each pipe dream, it comes with a permutation and a monomial. To find the permutation, you just write 1, 2, 3, 4 on top. You follow the pipes and read 2, 1, 4, 3 on the left. So these three pipe dreams are associated with the permutation 2, 1, 4, 3. To find out the monomials, you look at the crossings. So a crossing in row I gives you an xi. Now I see two crossings in row 1 that corresponds to x1 squared, x1, x2, and this guy is x1, x3. Now if I want to compute the Schubert polynomial of 2, 1, 4, 3, I first find out all these pipe dreams of 2, 1, 4, 3. And then I just go ahead and sum up their monomials. That's my Schubert polynomial of 2, 1, 4, 3. That's the first method of computing the Schubert polynomial in today's talk. The second method is the bumpless pipe dream rule given by Lamley-Shimazono fairly recently. So they now have a square grid, and then now the pipes go from bottom to the right. This time you have 6 different tilings, and then, but as before, we don't want to see double crossings. Now each bumpless pipe dream also has a permutation and a monomial. To read the permutation, you write 1, 2, 3, 4 on the bottom. You follow the pipes and read 2, 1, 4, 3 on the right. So these three are bumpless pipe dreams of the permutation 2, 1, 4, 3. To find the monomial, that this time you look at the blanks instead of the crossings. So a blanking row I gives you an xi. So here I have x1 squared, x1, x2, x1, x3. If I want to compute the Schubert polynomial of 2, 1, 4, 3, I just go ahead and find out all the bumpless pipe dream of 2, 1, 4, 3, sum up their monomials, and you see that that's the same answer as the previous slide. Now I'm going to tell you the story of Fomi and Stanley on pipe dreams. So what did Fomi and Stanley do? Well, they write down a generating function For pipedream, we all have seen generating functions, but here's a fun way to look at a generating function. So just imagine you walk into a fast food restaurant, you want to order a lunch combo, and you got 3 options for the entry, 2 options for the side, and you can either grab an ice cream or a drink. So whenever I see a menu like this, I just have one expression in my mind that is, I sum up the 3 entries, I sum up the 2 sides, and I have ice cream plus a drink. What's cool about this formula is that if I expanded this product out, I will have 12 terms. Each corresponds to 1 possible lunch combo. That just means I'm summing over all possible lunch combos. So that's a generating function for lunch combos. Now, for me and Stanley want a generating function for pipedreams, but creating a pipedream is the same as creating a lunch combo. You just go ahead and pick whether each tile is a bump or a crossing. That's your menu. So they just go ahead and write down expressions that look like this, but remember, a crossing in row I comes with an xi. But this expression doesn't make much sense right now because it loses the information of permutations, and it somehow doesn't remove those evil pipedreams with double crossings. So that's why they turn to something called the Neo-Cox tree algebra. So the Neo-Cox tree algebra is generated by U1 all the way to UN minus 1. The best way to think about the Neo-Cox tree algebra is that each monomial here is either 0 or it corresponds to a permutation in essence. So to find out this correspondence, we need to use this graph earlier. So now if I see U2, U1, the first U2 says, well, start from 1, 2, 3 and try to take the T2, 3 edge and go up. Well, now I'm here at 1, 3, 2. And then the U1 says, try to take the T1, 2 edge and go up. Well, now I'm at 3, 1, 2. So U2, U1 somehow corresponds to the permutation 3, 1, 2. So if you know reduced words, that's saying that S2, S1 is a reduced word of 3, 1, 2. On the other hand, this U2, U2 becomes 0. That's because the first U2 brings me here at 1, 3, 2. The second U2 tells me to take the T2, 3 edge and go up. I cannot do that, so that's just 0. And then for me and Stanley realized that each crossing actually behaves as if it's a U operator. So they realized that the crossing in the J's diagonal behaves as if it's a UJ. So right here, this is the 5th diagonal. And then if you think about having a crossing on this tile, it's actually switching the pipe going to column 5 and the pipe going to column 6 that behaves as if it's an U5. They can write down a generating function that look like this, where they go through these tiles from top to bottom and right to left on each row. And then a crossing becomes an xi uj, where I is the row index and j is the diagonal index. A bump, it just becomes a 1 here. If I want to create this pipe dream, well, that's the same as creating a lunch combo. I just go ahead and pick which term I pick on my menu. So I pick this term, and then this 1 term. I'm getting x1 squared, u2, u1. x1 squared, that's the monomial associated with this pipe dream. And u2, u1 corresponds to 3, 1, 2, which is the permutation of this pipe dream. On the other hand, if I have this evil pipe dream, which 2 pipes cross more than once, well, that corresponds to pick these 3 terms, and you see I have the term U2, U2, which becomes 0. So that's how for me and Stanley eliminates these evil pipe dreams. They just go ahead and write down some expression that look like this. So this is the case when n is 3, so that's what they have. It's a generating function over all pipe dreams where we have the monomial of the pipe dream together with the permutation of the pipe dream. That's a generating function, and they realized that if you want to prove the pipe dream formula for Schubert polynomials, it's enough to show that if I apply the partial I operator on these on this generating function, it will only affect these x variables. That's the same as right multiplied by ui. So once they can show this is correct, by the definition, by the recursive definition of Schubert polynomials, they know the PD formula is correct, so they give an algebraic proof for the pipe dream formula. What I want to do here is to give some kind of analog on bumpless pipe dreams. So now, well, for a bumpless pipe dream, we just have n squared boxes. And now our menu becomes bigger. We have 6 options for each tile. And we just have this huge product. And then somehow that we just have too much information. And many of them are bad. So in other words, there's a whole bunch of redundant information in a bumpless pipe dream. So the solution I'm going to do is to, well, I want to encode bumpless pipe dream using a tableau. I'm only going to look at these 3 types of tiles, but I also ignore the rightmost such tile on each row. So I will be only looking at 4 tiles in row 1, 3 tiles in row 2. So in general, I'll be looking at m minus I tiles in row I. So I can just encode this information using a staircase. So that will be like a tableau. I just go ahead and smash all the boxes to the left. And then if the box is empty, it remains empty. But if the box has a pipe in it, I write down the row index where this pipe ends up at. So this tile has a pipe that's going to row 1, so I just put a 1 here. This tile has a pipe that's going to row 2, so I put a 2 here. I'm turning each bumpless pipe dream into a tableau. Now you see a tableau in the token, you want to ask, like, what kind of tableaus can appear? Well, we first have this flag condition. So if I C and J in row I, that means there's a pipe going to row J, and it appears in row I. So of course, J is weakly less than I. What about the other conditions? Well, to describe that, we need to use something called the strong Broussard order. So we called this graph earlier, that's called a weak Broussard order, and now we have the strong Broussard order. So this time, it's strong in the sense that we have non-adjacent swaps. But keep in mind that we must, each swap must bring us one level above. So we cannot swap 1, 2, 3 and directly go to 3, 2, 1. That's not allowed. Another way to say this condition is, if I'm making a swap, I have to make sure that the numbers that are physically standing between do not have values between the two numbers being swapped. Well, now from each encoding, I can actually construct a chain in the strong Broussard order. So this is the encoding of this bumpless pipe dream. And then I will go ahead and read the same way as for me standing. I go from top to bottom and right to left. But this time I label these columns backwards. So this is column 5, column 4, all the way to column 1. And then I start from the permutation 5, 4, 3, 2, 1. If I see a 1 in column 2, I try to take the T1, 2 edge and go down the strong Broussard order. I can do that. So now I'm at 4, 5, 3, 2, 1. Then I take the T1, 3 edge, T2, 3 edge, T2, 4, and then T2, 5. I ended up at 3, 1, 5, 4, 2, which happens to be the permutation of the bumpless pipe dream I started at. So if I have a bad encoding, so this cannot be the encoding of any bumpless pipe dream. If I try to do the same thing, this 2 in column 5 says, well, I want to take the T2, 5 edge and go down in the strong Broussard order from the permutation 3, 4, 5, 2, 1, which actually is impossible. So I somehow know that if I cannot construct the Broussard chain this way, then this encoding just cannot be the encoding of any bumpless pipe dream. That's the proposition here. This is a bijection between bumpless pipe dreams and these tableau that, well, I have the flag condition, and then I can construct the Broussard chain based on the previous slide. Now I just need to go ahead and model these numbers using some sort of algebra. I turn to the Fomin-Kirchhoff algebra. This is the algebra generated by these Dij's satisfying certain relations that I cannot remember. You just need to know that it has an action on the permutations. And this action is denoted like this. So if you have Dij acting on the right of the permutation W, it just says, try to take the Tij edge and go down the strong Broussard order. If you can go down, just go. If you cannot, 0. That's similar to the new Cox tree algebra, where you were trying to go up in the weak Broussard order. Now we're trying to go down the strong Broussard order. And then we can just write down the generating function here. So now the size of our manual actually changes based on the row. So if you think about this box right here, by the flag condition, if it's non-empty, it must have a 1 in it. So if it's empty, then that corresponds to an x1 because that's like a blanking row 1. If it's not empty, then that's a 1 in column 2, so that gives me a D1, 2. That tells me try to take the T1, 2 edge and go down the strong Broussard order. What about this box? Well, it's in row 2, so it can be either empty, 1, or 2. So if it's empty, then that's an empty box in row 1 that gives me in row 2, so that gives me x2. Otherwise, if it's a 1, then that's a 1 in column 4 that gives me D1, 4. If it's a 2, that gives me D2, 4. So once I write it down, that's a generating function over all bumpless pipe dream where I have the monomial of the bumpless pipe dream together with the permutation of the bumpless pipe dream. Just like the PD case, if I want to show the BPD formula, I just need to check this algebraic equation where I apply the partial I operator on it. I just need to check it's the same as having the right action of a UI on it, where, well, now this algebra doesn't have UI, so we can just go ahead and define a UI action on things like this, where the UI says, try to take the Tii plus 1 edge and go up in the weak Broussard order. And then, well, I just go ahead and check this algebraically. This is just, I just play around with how to somehow swap these operators. And that gives us an algebraic proof of the BPD formula. But I'm not the first one who's trying to figure out like connections between pipes and Broussard chains. Lennard and Sotila actually can somehow convert a pipe dream into a chain in the Broussard order. So they go ahead and grab a pipe dream, and then they turn the bumps into crossings from top to bottom and left to right on each row. They got a whole bunch of pipe dreams, and they just write down their permutations. So I have this chain. And then it's miraculous that, well, actually each swap is actually bringing you up in the strong Broussard order. They also go ahead and put a label on these swaps. So if this change happens in row 1, they just go ahead and write down a pink 1 here as the label of this swap. So they got a chain in the Broussard order with some labels on them. What's cool about this label is that if you just go ahead and combine the swaps with the same label, like this, then this is actually what we call an increasing one chain. So this notion was first used by Sottile to describe the Pierre formula for Schubert polynomials. And then if you combine these swaps with label 2, then that's an increasing 2 chain. So in other words, Lenard and Sottile give a bijection between pipe dreams of W and chains that look like this, where you start from W, you take an increasing 1 chain, increasing 2 chain, all the way to n-2, n-1, and arriving at W0. Well, I'm doing something very similar here. I turn the bumpless pipe dream into an encoding, and then this encoding, well, I can have a chain from it. And then each swap in this Broussard chain actually comes from a number in my encoding. So if that number is in row 4, I can just put the label 4 here. If that number is in row 2, I can just put a label 2 here. What I can show is that, just like the Lenard-Sottile case, if I combine these swaps with the same label, I'm getting an increasing K chain. So this time, I start from W, and then I take an increasing n-1 chain, n-2 chain, all the way back to 1. So if you compare this, you can see that the only difference here is that I'm swapping the ordering of the labeling. So Lenard and Sottile would do 1, 2, 3, 4. But I'm going to do 4, 3, 2, 1. So in other words, I'm showing that pipe dreams and bumpless pipe dreams are somehow like a duo in this sense. Now here are the 2 analogs, and you might wonder, well, what are the applications? So one application is to give yet another bijection between bumpless pipe dreams and pipe dreams. So there already exists 2 bijections. The first one was given by Gao Huang, and then Knudsen and Udall, they somehow defined hybrid pipe dreams and give another bijection between pipe dreams and bumpless pipe dreams, and they can show that it agrees with the Gao Huang bijection. But now I'm viewing both things as these chains, and they already look pretty similar. So I wonder whether there is a way to go between these 2 types of chains. What I'm going to use is called the Lenard's growth diagram. So this is like a machine that eats an increasing 2 chain and then an increasing 1 chain, and it gives you something. And what I can show here is that it's actually giving me an increasing 1 chain followed by an increasing 2 chain in this case. So I can first grab a bumpless pipe dream, turn that into a chain where the labels are like 4, 3, 2, 1. Each arrow here with the label K just represents an increasing K chain. I use Lenard to go ahead and swap the 1 chain, and then eventually I can swap the 1 chain all the way to the front. Then I ask Lenard again to swap this 2 chain all the way to the front, and then the 3 chain here. And then now I have something from W to W0, where I take an increasing 1 chain, and then 2, and then 3, and then 4. That's a pipe dream by Lenard-Sottile. So that's another bijection between bumpless pipe dreams and pipe dreams. And I wonder whether that's the same bijection as the Gao Huang bijection. And now, sorry. Now you might wonder. What about these what about these chains in between? Well, actually, in fact, you can just go ahead and pick your favorite labelings. By the work of Sottile, actually, the order of the labelings actually doesn't matter if you want to compute Schubert polynomials using chains. So you can just go ahead and pick 2, 1, 3 as your labelings. You just go ahead and sum over all these chains where you take an increasing 2 chain, and then 1 chain, and then 3 chain, arriving at W0. That's also fine. If you make the vanilla choice 1, 2, 3, then that corresponds to pipe dream by the work of Lenard-Sottile. By my work, if you pick the other extreme, the 3, 2, 1 case, that corresponds to a bumpless pipe dream. But there are actually n-1 factorially many different options. So I might wonder, well, we have done a whole bunch of work on pipe dreams and bumpless pipe dreams. We have defined crystalgraphs. We have defined Monk smooths on them. We can use them to compute double Schubert polynomials. Is there a way to extend all these lovely stories on the 2 extremes to this whole family of n-1 factorially many different chain formulas? All right, that's all for today's talk. Thank you.
All right, are there questions for Tianyi? All right, Sarah.
So What new information do you get then about products of Schubert polynomials from looking at all the variations that you have?
Sorry, what's the
Did
question
you get
again?
any new information about multiplying two Schubs and expanding in the basis of Schubs? Can you say from all these different types of pipe dreams?
Okay, so the question from Sarah is that whether this is telling me anything about Schubert structure constants. So one thing I can say here is that this already behaves pretty similar to the skew Schubert polynomials defined by Lenard and Sotila. Yeah, it's somehow similar to the skew Schubert polynomials. So it might shed some light into finding some sort of pipe-like formulas for the skew Schubert. And we know that expanding skew Schubert into Schubert polynomials, that's giving you the Schubert structure constant. So maybe that's related in that sense.
Okay, I have a question, and then we'll get to Frank. So I was wondering, I didn't quite catch what you said. Do you think it's the same as the Gao-Wang bijection or not?
Thanks. So the question from Jessica is that whether this bijection is the same as the Gao-Huang bijection. So, wait, sorry, it's right here. So I computationally checked all the way up to S7. I somehow believe it should be the same. And then I actually have a reason for it. That is, Knudsen and Udall, they define something called hybrid pipe dreams. And in this picture, they correspond to 2 to the n-2 of these different chain labels. And then they just go ahead and gradually change their hybrid pipe dreams. They turn a PD into a BPD. And those, if you just go ahead and, I can somehow define another map from hybrid pipe dreams to chains like this, such that their hybrid pipe dreams will go ahead and turn, will correspond to these chains in between these two processes, which means, well, we just need to somehow verify that their algorithm of swapping two adjacent rows happens to be the same as applying the Lenard's growth diagram. So that's what I believe should be correct. So I somehow believe this bijection agrees with the Knudsen-Udall bijection, which agrees with the Gao-Huang bijection.
Okay. All right. Frank had a question?
Okay, so I'm mining an old memory, but I think there's a similar formula we have for K-theory, for Grothendieck polynomials, and the same mathematics behind those chain formulas should also hold for double Schubert polynomials, because it comes from just multiplying by certain symmetric functions.
Okay, so you're saying that there's like a chain formula for double Schubert, is that correct?
Well, I don't know, but the same mathematics should give you that.
Okay, so
there's certainly one for Grothendieck polynomials.
Okay, sure. So, got it. So the comment from Sotila is that, well, this might be related to double Schubert and Grothendieck polynomials, like this kind of chain formula should be related. Well, yeah, okay. I didn't think about that.
A question? Oh, it looks like Ashley sees somebody. Okay.
So is there an analog of this symmetric group Schubert polynomial story for like the affine symmetric group? Because you don't have like there is nothing on top somehow.
Could you repeat your question, please?
Okay, so is there an analog of this Schubert polynomial symmetric group story for like the affine symmetric group? Because somehow there's no longest element. Like, does this make sense?
Yeah, so the question is there an analog in affine world? I'm not that familiar with the affine world, but I'm pretty sure there's an affine Schubert polynomial, but I'm not sure how to compute it using pipe-dream, pipe-like objects.
Mm-hmm. Okay.
One more question?
Hi. Could you go to the next slide, the one with the different, yeah. So I guess each of these you can, so the original one you can think of as like you're putting a sort of total order on, if you take the lexicographic order on the transpositions that you're allowed to use, and you take chains that sort of respect that order, then you're saying pipe dreams sort of correspond to that. And then each of these other ones correspond to a different total order on the transpositions that you're allowed to have in your chain. Can you say something, is there something similar you can do for orders that are not just like sort of these sorts of rearrangements of this total order?
Okay, so the question is, well, what can I say about the other things in between? So first, well, the hybrid pipe dreams of Knudsen and Udall, I'm pretty sure they correspond to 2 to the n-2 of these labelings. So if you go ahead and define like a similar map from their hybrid pipe dreams to chains, well, that will cover 2 to the n-2 of such labelings. And then I guess in the work in progress with my collaborators, Gao and Zhang, so we do have some pipe-like formulas for the other for the other labelings.
All right, well, let's thank our speaker again.